The topic of today's presentation is improving speaker verification models for low resources languages. The development of speaker recognition technologies have a variety of motivations, including improving the accuracy and efficiency of speech-based human computer interaction and developing personalized services such as voice assistants and smart houses. The aim of the work is to develop an approach to perform highly accurate, comparable with performance of state-of-the-art models for resource-rich languages, speaker verification for low-resource languages like Ukrainian. The goal of this work is to study the efficiency of transferring skills of speaker verification from other languages, develop a robust speaker verification system, compare the efficiency of different approaches and algorithms. Base dataset, we have chosen Common Voice dataset. It's a crowdsourced dataset which contains a lot of data for low resources languages like Ukrainian. The Ukrainian split contains 73 hours of recording of 120 speakers in the train split and 14 hours of recordings of 639 speakers in test split. Additionally, in some experiments, we use recordings from other languages. The duration of recordings and number of speakers are shown on the slide. In order to extract features from audio data, we convert them to MEL spectrograms and treat them like an image data. As a key metrics to evaluate models' performance, we have chosen equal error rate, which is the most common metric in the field, precision in top K, which represents how many samples of the same class are present in top of similar samples. In our experiments, we have chosen K equals to 3, 4, 5, and 10. Mean and standard deviation of positive similarity. Positive means between original data recordings and recording with the same class as the original, and mean and standard deviation of negative similarity. Negative represents samples which belongs to other speaker than the original recording. We can see the plan of experiments in order to achieve the goal of the research. In first experiment, we compare different models architecture and different sizes in order to determine which one is most suitable for the task of speaker verification. In second experiment, we compared different loss functions, including triplet loss, arc phase loss, and subcenter arc phase loss, and the combination of previous three losses. In third experiment, we compared best model from previous experiments with model trained on multilingual dataset. The validation were performed only on Ukrainian dataset. In first experiment, we compared best model from previous experiment with a model trained using dog pipeline, which is a state-of-the-art approach in task of face recognition. This task from computer vision is similar to speaker verification, so we are trying to analyze the possibility of transferring skills in audio domain. And in fifth experiment, we studied how the data augmentations affect the model performance and robustness to new data. This model for our experiments, we have chosen ConvNext architecture, which shows superior results in some computer vision tasks, and we assume that these skills can be transferable to the domain of speaker verification from MEL spectrograms. We can see how the loss function on validation dataset were changing during the training during the first experiment. We compared ConvNext small and ConvNext tiny. As we can see, the loss function stays approximately the same for both models. So we have chosen to continue our experiments with tiny model because it contains less parameters, so it can be trained faster, so we can perform more experiments in a shorter amount of time. With that, we can see the results of second experiment. All networks perform approximately the same, but as we can see, models that were trained with triplet loss perform a bit worse and reach plateau a lot more faster than networks that were trained with pure arc phase and subcenter arc phase. See the results of third experiment. As it is shown on the slide, models that are trained on multilingual dataset show better performance than ones that were trained only on Ukrainian data. But after several epochs, models that was trained on the on unbalanced data seems to overfit. So in order to achieve best transference skills from other languages, training data from other languages should be approximately the same size as the data from original language. See the performance metrics on the fourth and fifth experiment. We can see that DOLG pipeline shows superior results over the other networks, and data augmentations leads to better robustness to new data points. And in general, this approach helps us to achieve state-of-the-art results in speaker verification. After the training, we test our model in the task of speaker diarization on real-world data. Especially, it was a Google Meet meeting between and dialogue between two peoples. On the side, you can see the TS and E projections of voice embeddings that were generated by the model and clustering results. As we can see, there are two clear clusters with some boundary region, which may represent the fragments where both speakers speak at the same time. Also, you can see the speaker diarization example where the results of the model were converted into standard subtitle format and shown that from a specific period of times, one speaker set, and from other period of time. To conclude that were mentioned above, in the first experiment, the results of both convex tiny and convex small are quite similar, so it was decided to use convex tiny because it has less parameters, so following experiment can be performed faster. In the second experiment, all networks perform approximately the same, but losses that contain triplet loss perform a bit worse than arc phase and subcenter arc phase. In third experiment, multilingual model show a superior matrix on test set than achieve better results in general. In the first experiment, DOLG shows superior result and pretty much achieve state-of-the-art result in task of speaker verification. In fifth experiment, we applied augmentation to spectrograms and repeated the previous experiment. As a result, the model achieved even better level of performance and robustness. So, in conclusion, we recommend to use Next Tiny as a backbone in the DOLG pipeline to achieve certain results for speaker verification in Ukrainian language. The study demonstrates the effectiveness of deep learning models into the task of speaker verification, even for low resources languages. Also, it provides insights into best performing network architectures and functions for this task, and shows the potentials for transferring skills from other languages to low resources languages. This perspective of further studying includes comparing of large amount of convolutional neural network architecture, especially with large number of parameters, different loss functions, and their combination. Also, it's quite important to study transferring learning from other languages and perform multilingual speaker verification. That's all. Thank you for your attention.